levitate, 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 levitate.
In this video, we're going to be talking about how we went about levitating a magnet with a feedback control loop. We'll start off with a general overview of the process and our components, and then get into a little bit of the theory behind our loop control. Then we'll finally share our results with you.
This must be real magic. This is crazy.
So here we have a simple free body diagram of a magnetic levitator. On top is a solenoid producing a magnetic force, pulling the magnet up, and then the force of the gravity pulling the magnet down. The idea here is to have equal forces to keep the magnet in equilibrium at a set point.
We designed this structure to hold our system and allow enough clearance from the ground for a sizable object to experience levitation. To lift the magnet, we needed to find a solenoid, and we started off by ordering this push-pull type electromagnetic solenoid. Its 2.1 kilogram force just wasn't enough to lift a decent sized object, so we purchased this spool of 22 gauge wire. The more turns this wire has results in the more magnetic force from our solenoid, which allows us to use a wider range of weighted objects. We then ran a long bolt through the core of the spool and secured it to the top of our structure. After that, we needed to define the eyes of the system, that is, the sensor. We chose to use a Hall effect sensor. The Hall effect works by running a charge through a metal plate, then introducing a magnet. When we introduce a magnet to the plate, the positive and negative charges separate to opposite sides, producing a measurable voltage. We then use the measure of that voltage to gauge the distance of our magnet. The sensor itself uses the outside two prongs to run a current and the middle prong as a ground. Next, we have to find the perfect item to levitate.
Turn myself into a pickle, Morty! Boom! Big reveal, I'm a pickle. What do you think about that? I turned myself into a pickle! I'm Pickle Rick!
So Pickle Rick is just awesome, but we're going to tell you that we chose him for his axial symmetry. We drilled holes in the top and bottom of our pickle and glued in our magnets. After we figured out our object, the last thing we were missing was control. We had our input and output, our sensor and our process, and decided to incorporate a PD controller for a few reasons. To explain a little bit more about this process, here's Thomas.
Don't do it.
So basically we decided to do a PD controller that would work best because we needed the ability to adjust our system's poles and at a 0 to stabilize our overall closed loop feedback system. You'll see in the schematic an analog PD controller utilizing a pair of op amps to amplify the Hall sensor's voltage output. We chose to go with the analog route to avoid having to program an Arduino and create a printed circuit board, but also because we invited the challenge of a fully electric design. To this, we had to do multiple permutations of resistors and capacitors layouts to get the right combination. There were a couple struggles we faced with this. We had difficulty achieving 0 voltage on our ground rail, which prevented the solenoid from powering down and prevented the op amps from truly operating correctly.
We then had to solder on the wires at multiple connection points to fully incorporate the components of our system.
Where's the screwdriver? Is that a screwdriver? Oh.
Just making sure you got yours.
After a little bit more tweaking, we felt we designed the perfect system for Pickle Rick to get off the ground. We ran the numbers. We put in the hours. We made the tests. The moment was finally here.
Pickle Rick!
But sometimes it just doesn't work out how you want it to. What do you think of that, Ross?
No way.